Welcome to our next lecture on the Internet of Things. In today's final lecture on the topic of data, we'll talk about data storage and processing for the Internet of Things. So, to look at our overview diagram again, we have two places in which data is processed and in which data should be stored. So on the one hand, we have IoT data fusion in the middle here, which we already talked about a bit regarding the topic of sensor data fusion. And of course, we want to store data, and data is usually not stored on edge devices, but somewhere on the other end of our IoT networks, so somewhere in a cloud system. And we're going to talk about special approaches, special infrastructures that help to store data in IoT systems. So to give you an overview of databases which are traditionally used to store data, first, you might know relational databases already, something like the big databases from the manufacturers like Oracle, or smaller open source databases like MySQL. And these are so-called relational databases, so they're based on a schema, and they usually support the SQL or SQL query language to access and modify data stored in a database. A development that has been rejuvenated recently is what we call NoSQL databases. So NoSQL is one of the differences between these databases and relational databases. So they don't support the SQL query language in general, but what's more important is that they have a different structure. So there are non-traditional database approaches compared to relational databases. But we need to mention that NoSQL databases also have existed before relational databases were invented sometime back in the 1970s. So NoSQL databases come in a number of different forms. So we can have very simple approaches like key value stores, where you just have a key, which is a unique identifier, and then we have a value for this, like we have a name and then your name for exactly every entry in our database. But we can also store more complex data, which is difficult in relational databases. So we can store documents. We can also have something like wide column stores, time series databases, which is especially interesting for IoT applications, and also graph databases. And we could also have something that would be able to process data as it's streamed. So this might be an interesting approach also for especially IoT data, where we have updated data coming in all the time. So essentially, we want to be able to extract data from this stream of data passing by without maybe having to store it all the time. So relational databases are based on the relational data model. That's why they're called that way. So in relational databases, data is organized into what we call tables. So we have one or more tables, and a table is a relation of columns and rows, and each row is identified by a unique key. So the rows are also called records or tuples, and the columns are usually also called attributes. And each table or each relation represents one so-called entity type. For example, we have a table for customers, like this customers table might include the name, the address, the phone number of a customer, or we have a table for products, which might include your product number, the name of the product, the quantity it's delivered in, and the price of a product. And usually relational databases use a standard query language, the standard query language SQL, or as it's called in America, SQL. Now, the problem with relational databases in IoT context is that the amount of data that we need to store for IoT applications in the back end, so not in each sensor node, but back when we accumulate all our data, this might become so large that it's very impractical or even impossible to process this using a traditional relational database. For example, this might be user-generated content in social networks, so we have like thousands or several thousands of tweets coming in every second in Twitter, or, of course, data retrieved from large sensor networks where you have thousands of sensor nodes. And running this in a relational database is very impractical. This general trend is also called big data. So big data is something that requires new approaches from database designers and database manufacturers. Now, what are the challenges when we want to store data in the IoT? We have a number of problems here. So data in IoT applications is characterized by its heterogeneity. So we might have very different forms of data that we want to store and process. We might have variable data formats. So we already mentioned that we might have different manufacturers with like different approaches to storing and processing data in our complete IoT system. So we have to handle this variability in data formats. We might have real-time requirements, so we might have to react more or less within a given amount of time to data coming in. So we can't just store it and then retrieve it again an hour later, but we should probably be able to introspect the data as it's coming in. And related to this, we have data streams, and we also want to support data fusion. And as we already mentioned, traditional relational databases don't cover these IoT use cases very well. They make it very difficult to support these heterogeneous data structures because we're always fixed to this table or record format here. It's very difficult to store large data like blobs, like a picture from a camera or video or an audio stream inside of a relational database. Uh, the relational databases usually don't give any real-time guarantees. So if we have real-time applications, we cannot really guarantee when a query on the database actually returns any useful data. And finally, we might have streaming data, and streaming data that might be possibly only relevant for a short amount of time, and then we can discard it. Relational databases are usually made for long-term storage of data and not for just continuously updating and removing data sets from the database. So that's why NoSQL databases were introduced also in the IoT. So they have been used in several different contexts before, especially in very many web databases. For example, if you want to store a blog, and the blog article isn't really well suited for storage in a relational database. So NoSQL databases are just a common term for a class of non-relational databases, which cover a wide range of use cases and specifically includes databases able to cope with this big data we've been talking about before. So many NoSQL databases offer what we call horizontal scalability, and they also offer higher availability than relational databases. But we are sacrificing some querying capabilities, some consistency guarantees that are provided by traditional relational databases, but maybe not needed in all application cases. So these trade-offs are important for service-oriented computing and X as a service model, so software as a service or platform as a service, because any stateful service can only be as scalable and fault tolerant as the underlying data store. So essentially, when you use a NoSQL database, you might have to invest more work in getting your infrastructure right and appropriate to your use case, but then you get the reward of being able to handle more complex data, handle data in real time, handle larger amounts of data compared to relational databases. So in NoSQL databases, we have what we call the storage pyramid here. So we have different levels of storage in the storage hierarchy, and NoSQL databases are able to integrate these storage levels. So we can choose between storing data in very fast, expensive, and small memories, which would usually be main memories. So there's a whole bunch of research on main memory databases. So obviously, main memory is very fast to access. But of course, when you look at the costs per gigabyte, for example, a gigabyte of RAM costs about $5 to $8 right now. And so you don't want to include like terabytes of RAM into your computer. First, there might be physical limits, like the number of available slots for RAM modules, the number of available physical addresses, and of course, the amount of money you actually want to invest. So usually a current computer has like several gigabytes of RAM, and machines with like more RAM, like in the terabyte range, tend to be very expensive. So that's why we introduce different levels of storage. So we have very large and very slow storage. On the other hand, the traditional hard disk drives, mechanical hard disk drives, so these come in terabyte sizes and are relatively cheap, but they have a problem. First, they are mechanical components, so they are prone to fail. Second, they are slow because they relate on mechanical components to move, like the read-write head that has to move from the inner part to the outer part of the hard disk to access different data. So this takes time. This mass of the head has to be accelerated, it has to be break down, and of course it needs time to move on the disk. And you have the rotational delay of the disk, so the disk just rotates under your disk head. So hard disks are very slow, but they're very inexpensive, and you can buy just a whole amount of them. And you can also make it redundant by introducing technologies such as redundant arrays of inexpensive disks, RAID technologies. We're not going to discuss this in detail here. So what's happened in recent years is that we now have an intermediate storage layer, which is not as slow as SSDs, but it's also not as slow as HDDs, hard disk drives. It's not quite as large in common cases, and it's a bit more expensive. So it's somewhere between hard disks and RAM, and that's of course, as you already probably know, the SSDs, so the solid state disks. So in contrast to hard disks, we now store our data in, well, flash memory, like you use from the SD cards in your cameras or MP3 players or phones. And these flash memories are relatively inexpensive compared to RAM. They're relatively large, but they're an order of magnitude or more slower than RAM. So this is an intermediate layer which might help. And accordingly, we can distribute several tasks over this memory pyramid or memory hierarchy here. So for example, we could use RAM for caching, for the storage of primary data and the structure of data. We could use the SSD for caching, logging, and also primary storage. And then HDDs are usually just used for all the things which don't need to be that fast, so you're storing huge amounts of data here. So very often NoSQL or NoSQL databases can make use of the storage hierarchy, but it's up to you to actually configure the use of the components in your storage hierarchy. So let's look at different types of NoSQL databases. First, we look at key value stores. So key value stores are very simple. So they just consist of a set of, well, pairs of keys and values with the restriction that the keys have to be unique. So this is very simple, and accordingly, the operations supported are also very simple. So you only have a get operation where you supply a key and you try to figure out if there's any key in the database and if it has any value. And if there's any value, it's returned to you. And on the other hand, there's a put operation. So a put operation provides a key and a value and then tries to insert this key value pair into the database. So the pure key value stores in their simplest form do not support operations beyond what we call CRUD. So we create something, we read something, we can update something, or delete such a key value pair from our NoSQL key value store. Key value stores are what we call schemaless, so you don't have any assumptions about the structure of stored data in the database itself. So in a relational database, you might have records. So a customer record might have a name, an address, and a phone number. All these relations are not visible in such a key value store. So you'd have separate keys for names and addresses, for example, and phone numbers. And then your application logic actually has to make sense of it. So the combination to indicate that name, address, and phone number belong together has to be a part that has to be explicitly coded in your application and not provided by the database. This makes it more flexible, but of course, it also creates higher demands to the application developer. Now, sometimes we want to store more complex data. So another sort of NoSQL database is what we call document stores. So a document store in general is also a key value store, but with very special values. So the values we store can be large, and they're restricted usually to semi-structured formats. One example for this, which might be very useful for ID use cases, are JSON documents. We've seen JSON before in our discussion about data formats on the IoT. So we might have some keys here and a accordingly assigned to this key is a complete JSON document. So as you see on the picture on the right-hand side, this might again introduce a structure into our database, but the database doesn't know anything about it because the database isn't aware that this is a JSON document. So again, your application has to take care of it, but it's a way to actually introduce such a thing and then, well, make use of it. So this is a restriction in comparison to regular key value stores, as we've seen on the previous slide, but it brings great flexibility to access the data because now we have something like document IDs, which are stored in the key. So we can not only fetch an entire document by its ID, but by having a JSON structure on the right-hand side, we can now also retrieve only parts of that document here. For example, we can retrieve the age of a customer, and we could then execute queries like aggregate or query by example, or even do a full text search over our JSON documents because they're just encoded as ASCII documents and not in a binary format. Obviously, there's some overhead involved because we have JSON as a document format here now, but sometimes the ease of working with this makes it worthwhile. Another type of NoSQL databases are white column stores. So they're named according to the underlying data model, so a relational table here, but we have a large number of sparse columns. So technically, a white column store is closer to what we might see from data structures as a distributed multi-level sorted map. So we have keys on different levels. First level keys can identify rows, and the rows themselves can then be key value pairs, as we've seen before. So we have row keys and we have column keys, and that enables this sparse data storage so we don't have to store don't have to reserve storage for information which is just not contained in the database because we don't need it. So this storage scheme makes tables with arbitrarily many columns feasible because there is no column key without also providing a corresponding value. It's like storing a table or a matrix with very many empty elements or null elements in a matrix by only storing the information about which of the x, y coordinates actually contain values, and then just giving these as key pairs here. So this means that when we have null values, so non-content values, because there's no content for a given combination of row and column, for example, we can store them without requiring any space overhead because this information just isn't there. Now, another point that's very interesting, especially for IoT applications, is a specific type of database, which we call a time series database or just TSDB. So a time series database is a software system optimized for storing and serving time series, and this is made possible by a basic data type, which is a pair of a time and an associated value. So this could be an absolute point in time and an associated sensor reading, for example. So time series data sets tend to become relatively large, but they are very uniform. So it's just a timestamp and, for example, a temperature value here. And this is what distinguishes them from other data sets. Time series databases usually also have fewer relationships between data entries in different tables because, the most important relationship is actually the point in time, which is implicitly there. And usually time series databases don't require that we store data indefinitely. So sometimes it's sufficient, like after we've read some data, to just store the median or mean value of data or just throw it away because we don't need any data older than, let's say, 10 seconds old. In some fields of applications, time series could be called profiles or curves or traces or trends, no matter what they are called, like for example in financial data or in traditional physics data processing. The time series is the basic information that's processed here. So if you remember back to our lecture on sensors, we have our discretization of sensor values in the time and value domain, and this time discretization is exactly what's handled here by providing a discrete point in time as an index here as the key, and then the discrete value we obtained as the value to store here. And there's a number of IoT based databases out there handling time series. One example is Apache's IOTDB, which we show on the right here as a sample for a query and what's possible. Now, finally, we have another sort of database which might be interesting for IoT applications, and this is graph databases. So, a graph, as you probably know from your computer science education, is a data structure consisting of two distinct parts. We have nodes and we have edges. So, a set of nodes is connected by a set of edges, and these edges define possible connections or data flow or whatever you want to model inside of a graph. So it defines a connectivity inside of this graph. So a graph database obviously is a database based on modeling data as a graph, so on graph theory, and the objects which are processed by a graph database consist of nodes and edges. So nodes in a graph database represent entities or instances, and this can be people or businesses or accounts or whatever you want to be tracked in your database. This is the rough equivalent of a record or relational row in a relational database or a document in a document store database. And then the edges connecting the nodes, well, these indicate the connectivity inside of your database. So it represents a relationship between the nodes. So for example, if you store customers and whatever providers of goods, so sellers in a database, you might have a relationship in this graph database, and you see it's indicated very often by arrows, so you have a direct relationship, and you might have a relationship from a customer to a seller of items. So this might be a relationship that obviously a seller of items has many customers, and these might all be linked to the seller in a database here. So as we've seen, these edges can be directed, so we indicate this by using arrows here, but we might also have cases with just an undirected edge, which is just a connection, just a line without any tip of the arrow here. So in an undirected graph, accordingly, an edge connecting two nodes has a single meaning, whereas in a directed graph, the edges connecting two different nodes can have different meanings depending on the direction. And obviously, edges as the means to indicate connectivity are the key concept in a graph database. They represent an abstraction that's not directly possible to implement in a relational or document store model. So it's very useful, for example, to describe hierarchies of data flow in a complex sensor network, to describe connectivity in networks, stuff like this. Finally, a third thing which is important in a graph database is what we call properties. So a property is a piece of information that's associated to a node. Now, for example, if Wikipedia was a node, it might be tied to certain properties in our database, such as it's a website, it provides reference material, or it's also related to a property which describes all the words that start with the letter W. So graph databases are still an active research topic. There's a number of these out there already, and I assume there are a number of interesting use cases, especially in an IoT context here. Here is an example to capture the structure of IoT systems in a smart home environment, taken from this publication we linked here. And this could, for example, be used in a graph database called Neo4j. So you see, we have some entities, and we have essentially something that models our house, like doors, rooms, offices. So we have a hierarchy here. So for example, we have rooms, and one of the rooms is an office, and a room can be connected to a door, which also is an exit. And then on the right-hand side, we can have different companies in our smart office building, for example, on different floors, which occupy different offices. So we have relations from companies to offices here. So a company can have offices rented on different floors. So a company can be on a floor or on different floors. Offices are on floors. And of course, offices are related to companies. And then related to the offices, we might have some assigned fire exits here. And then assigned to the fire exits are some sensors and actuators, like smart plugs, like door locks, and so on. So this is just an example of a structure we might want to model in such an IoT graph database here. Of course, there's a number of additional examples, so please refer to the literature here for more information. Now, of course, the IoT is a distributed system. So essentially, we want to enable distributed data storage and processing also in an IoT system because, well, the centralized point of data storage is on the one hand is well, single point of failure. So if a distributed database fails, well, no, if a non-distributed database fails, then of course your whole system is unable to operate. And of course, distributed databases are also very useful to load balancing in the case of high loads. So, as an example, Cassandra is a distributed wide column store NoSQL database, and it's designed to handle large amounts of data across many commodity servers. So you can put a large number of servers or virtual machines out there in the cloud, and you can distribute your database over all of these. And this has the advantage of providing high availability with no single point of failure. So even if one or more of your servers go down, your database will continue to work, something that's obviously very useful in an IoT context. And this supports clusters that span multiple data centers, and you can also have replication between these. So essentially, a high availability solution that's possible. Well, and probably a pretty good approach if you have high high amounts of data and high availability requirements in your IoT applications. So if you're interested in this, please take a look at the background information on Cassandra. So the big question is, if you want to use a NoSQL database in your IoT application, the question is really, which one should we use? Because we have so many different ones and they're just characterized by this common property that they're not a SQL, not a relational database. So that's why I provided a NoSQL decision tree here from a paper that was published a few years ago. And this considers different trade-offs here. So in the leave notes, we have applications from simple caching on the left to big data analysis on the right, and we differentiate according to access patterns on the one hand, query complexity on the next level, and the volume of data. So on the top level, we check if the access we require should be fast, so we need fast lookups here, or if we want to support complex queries, accordingly we go to the left or the right. Now, let's first consider fast lookups here. So if we have essentially just small volume here, which fits into RAM, we can use a RAM database like Redis or Memcache. If we have an unbounded volume of data, so we need to go to external storage, we can check Cassandra or, on the other hand, non-distributed use cases like MongoDB, Couchbase, or DynamoDB. And if we look at the right-hand side, if we need complex queries, again, we can look at volumes. So essentially, we have the amount of data that fits on a hard disk drive. Then we can differentiate between consistency requirements and have traditional relational database models, Neo4j, and so on. Or if we want availability as the more important factor here, we have again Couched and MongoDB here. And when we need unbounded volume of data here, then we want to look at query patterns here. So we have analytics. So we want to get more structured data out of it. Or we want ad hoc queries that can be, well, very diversified. So there's a number of options here. We can't discuss all the options here in the context of this lecture, but as you see, there's a large amount of options out there, and this decision tree and the related paper might be an interesting reading if you have the task of finding and implementing a database for your IoT use case. So here's another graphic that shows the properties of different NoSQL databases in a context here. So we have three properties: consistencies. So consistency means that all clients of your database see the same data at the same time. Sometimes this is very much required. For example, if you do inventory checks or flight bookings, then of course, if like if you do a flight booking for the last seat on a plane on one database and the other doesn't see the update and still sees it as free, Even though the seat is taken, then you have an overbooked plane, for example. The same for inventory. If you sell the last piece of product on your shelf twice, then you might run into problems here. The other dimension is availability. So availability means that the system continues to operate even in the presence of the failure of one or more nodes. And the final one is partition tolerance. So if you happen to have a distributed database and you lose network connectivity between parts of your service in your database, then the question is if your system is able to continue to operate here. And you see there's a large number of database solutions out there supporting this. And depending on what you need, consistency and availability, consistency and partition tolerance, or availability and partition tolerance, you have a number of solutions. There's no real solution fitting in the middle, and the intersection of all three, that would be a too complex solution, I guess. So to conclude our discussion of databases in the IoT, we've seen that traditional relational databases in many cases are not that well suited for our variable, streaming, heterogeneous, and big data use cases in the IoT. NoSQL databases are just a name for a class of databases, and we have very many different types of databases for specific use cases, like key-value stores and document wide column stores, time series databases and graph databases. And if we need availability or load balancing or similar use cases, we can have distributed databases that help us with this. But of course, these might be more complex to implement and to use. So finally, here's a set of references as always. So we start with a reference on relational models of databases. So this paper from 1970 by Cott was the basis of all these SQL databases we've seen. And then there's an overview of non-SQL databases, surveys and decision guidances, and different papers about different approaches to the types of databases we've discussed so far. So that's all about databases in the IoT. Thanks for listening, and until next time, bye.